The integration of artificial intelligence across multiple domains has emphasized the importance of replicating human-like cognitive processes in AI. This work develops a methodology for modeling psychological disorders using reinforcement learning (RL) agents, incorporating emotional intelligence to evaluate their emotional stability and enhance their resilience in critical decision-making tasks. The authors propose an appraisal-guided proximal policy optimization (AG-PPO) algorithm, which utilizes appraisal theory to train RL agents in a dynamic grid world environment. The AG-PPO algorithm is designed to simulate psychological disorders, such as anxiety and obsessive-compulsive disorder (OCD), by regulating the behavior of agents through various reward-shaping strategies. The authors compared different configurations of the modified PPO algorithm, identifying variants that simulate anxiety and OCD-like behavior in agents. They also compare the standard PPO algorithm with AG-PPO and its configurations, highlighting the performance improvement in terms of generalization capabilities. The authors formulate 6 cognitive appraisals obtained from the grid world environment, representing the psychological state of the agent. These appraisals involve subjective evaluations of personal significance and implications of events, which are difficult to quantify and represent computationally. The AG-PPO algorithm effectively grasps and uses diverse appraisal dimensions, bridging qualitative appraisals with quantitative RL. This study introduces a novel approach to reinforcement learning by incorporating cognitive appraisals into the Proximal Policy Optimization (PPO) framework. Cognitive appraisals are variables that influence an agent's decision-making process, including motivational relevance, novelty, certainty, goal congruence, coping potential, and anticipation. These appraisals are estimated at each agent step and are used to shape the agent's actions and value estimation. The study defines each appraisal variable mathematically, using equations to calculate their values based on the agent's position, goal state, and other environmental factors. For example, motivational relevance is calculated as the complement of the Manhattan distance between the agent and goal in the grid world, while certainty is estimated using the entropy of the soft-max applied output of the actor network. The study also introduces a reward-shaping strategy, which modifies the immediate rewards using cognitive appraisals to guide the agent's learning and exploration. 10 different configurations are experimented with, including a baseline and control, as well as multiple variants using reward shaping. Each configuration is designed to test the effectiveness of different appraisal variables and reward shaping strategies. The study adapts the standard PPO algorithm by incorporating cognitive appraisal variables into the critic network. The modified approach uses a convolution network to process state information and appraisal variables, which are then used to estimate the value function. The policy loss is estimated using the clipped surrogate objective function, which measures the policy's deviation from its previous policy. The study also presents an algorithm for the modified cognitive appraisal-guided PPO, which includes initialization, observation, action selection, and policy updates. The algorithm uses generalized advantage estimation (GAI) to estimate the advantages, which are then used to train the actor and critic models. Overall, this study introduces a novel approach to reinforcement learning by incorporating cognitive appraisals into the PPO framework. The study demonstrates the effectiveness of different appraisal variables and reward-shaping strategies in improving the agent's performance and adaptability. The integration of cognitive appraisals into reinforcement learning agents enhances their performance and generalization in grid-world environments. The RSV1 configuration, incorporating motivational relevance for reward shaping, outperforms the baseline and PPO plus appraisal configurations in both GWA and GWB environments. Equation 19 computes the overall score, with Table 2 summarizing scores for all configurations. RSV1 emerges as the top configuration, excelling in both environments. Cognitive appraisals, such as stress, aversion, and distraction, are analyzed using Equation 20 and behavioral indicators. Table 1 demonstrates that the RSV7A agent exhibits repetitive behavior patterns resembling OCD symptoms, including adherence to non-contributory action sequences, heightened distractions, and stress. This suggests the presence of anxiety and OCD-like traits, driven by internal compulsive tendencies. The RSV-7B agent's preference for grid edges reflects its cautious avoidance behavior, resembling traits seen in anxiety disorder. The research draws on a comprehensive literature review, spanning psychology, neuroscience, computer science, and engineering. References cover emotion regulation, cognitive antecedents and consequences of emotion, affective computing, reinforcement learning, deep learning, and natural language processing. The importance of emotional intelligence in human-computer interaction and the challenges of developing emotional AI systems are also discussed. Specific applications of AI, such as reward shaping and image recognition, are cited, along with papers on psychological and neurological disorders, including OCD and generalized anxiety disorder. The literature review highlights the complexity and interdisciplinary nature of the research, providing a solid foundation for the development of novel AI systems that can understand and interact with human emotions. The integration of cognitive appraisals into reinforcement learning agents demonstrates promising results, with potential applications in human-computer interaction and AI systems.